Guess we're done. Someone logging on right now. Okay. Excuse me. We'll get started. We're going to get into the second half of the pavement mix design, which is pertaining to asphalt. Okay, asphalt, not asphalt, as I was noted last week. Okay. First of all, what do you guys think of the quiz or the exam, whatever you want to call it? Pretty short though, eh? A lot of people are finishing way too early. Okay, I can make it up on the asphalt. That'll be that much tougher. Okay. Ray, can you, if you hear me, can you put your video on? I want to introduce you. Okay, we've got Raynan Cornell. He's joining us. He's our educational assistant, I should
Hello.
say, working in the lab. Hello, Ray. Ray put together, we'll be reviewing it a little later, video and actual mix designs. And he's over in B109 right now, getting things ready, cleaning things up, until such time as classes start again in the fall. He's in temporarily as Jody is on maternity leave. So Ray, you graduated from this course 2 years ago, 3 years ago?
Yeah, 2019.
2019. So Ray is a graduate of the Pavement Mix Design of the municipal, same as you guys. So if you have any questions, Ray's very familiar with pavement mix design, especially in the asphalt end of it. He's now working in industry also. Took a little bit of leave of absence, and when Jody comes back, I would imagine he may be moving back there unless he finds something other than that.
We'll see.
We'll see. Yeah. Okay.
Okay, thank you.
Yeah. So Ray's around. If you guys need to reach out to him, by all means. His email address is same format as mine. It'd be raycornell@rrc.ca. Okay.
It is actually rcornell@rrc.ca.
It's what? R Cornell?
Yeah,
Isn't that what I said, or what did I say?
you said Raynan.
Oh, sorry. It's R
Don't worry.
Cornell
Yeah.
at rrc.ca. Same format as the instructors. Okay. Okay. We're going to get into asphalt, sometimes referred to as HMA, hot mix asphalt, sometimes referred to as HMAC, hot mix asphalt, asphaltic concrete. Okay, HMAC. So these are all terms that are used in the industry. It's concrete because it's got a binder, just like Portland cement, Portland cement binder with aggregate. Instead, we're using asphalt cement. And it's not oil. Don't use the term oil. If I see you guys using oil in your notes, I'm going to deduct marks. Not oil. Asphalt cement is a byproduct from the distillation or the refining process of crude oils. And what's left over is the residue after you take off your gasoline, your diesel, your naphtha, the lubricants. So we're left with what's the bottom of the barrel, as they call it. Okay? And that's crude. That's residue. And that's what gives us. Do not call it tar, because tar has been used and in some countries is used to make pavements. And we use tar prior to the refining process, but we don't use it anymore. And we'll get into that a little bit. So the pavement mix design on this one is aggregate, asphalt cement. Some of the newer mixes have modifiers in it, rejuvenators in it. And recycled asphalt is used with virgin asphalt in many, many mix designs, more so than what concrete was. Recycled asphalt pavements have been used quite extensively for many years now, say, as compared to the Portland cement concrete. Okay, so I'm going to kind of give it a little bit of an introduction. I'm going to show a little sketch here, and it's taken out of one of the other units we'll be studying. But I'm getting somebody's feedback. Somebody's mic on? Okay. If you want to speak, that's fine. But if you're just listening, maybe just keep your mic off because we're picking up background noise. And then we'll take it from there. We'll look at the little sketch here. So I'm going to share a few things here, and let me know if you can see them or not. So got a few of them all listed
John,
here. Yes, sir.
can you hit record?
Oh, you betcha. Thank you very much. It was just an intro, so it's not much there. Record on my computer. Betcha. Thank you for the reminder. I've got a good memory, guys, but it's short. That's what happens when you're aging. Just put on the computer. Okay. So let me tie it in here too. Give me a minute here, guys. Okay. Sorry about that. Okay, let's get back into the. This isn't. Okay. This is a crude sketch, but here we're looking at asphaltic pavement. If you just took some aggregates, dumped them into a pail, just like whether it be concrete aggregate or whatever, but this is asphalt aggregates. So if you dumped it into a pail, you'd see this here on the left-hand side, this left sketch. Okay, you've got aggregate with voids in it. My mistake. Middle one, sorry. I should have had these turned around. But anyways, if you took straight aggregate and dumped it into a pail, you'd have aggregates with voids in it. Now, if you took some asphalt cement and it was heated, so it would be flowable, and you dumped it into the pail, you would get the asphalt cement seeping down and coating some of the aggregates. Hopefully you'd coat most of them, but you're still going to get voids in between that don't get filled with asphalt cement. If you add more asphalt cement, eventually you could fill them totally, but that's not what we want. You're going to find out later on as we look into this that what's very key, the performance of asphalt, is that you have a good distribution of aggregate, you have a good coating of the aggregate, but you also have air voids that aren't filled with the asphalt cement. You need that. And we'll look at some of the effects later on if we don't have it. So if you took a schematic look at it, this is what you would have. This is almost like what you guys took in geotechnical materials 1 with Natalie when you did mass void, mass density relationships. Here we're looking at what asphalt mix would look like. You've got aggregate, you've got the asphalt cement, and you've got some of the air voids that aren't filled. And this, like in this picture on the left here, you've got the asphalt in there, but you also got air voids. So if you looked at this, you could say we have aggregate and we got VMA. Does anybody have an idea what VMA would stand for? What does VMA indicate? Anybody you want to take a guess at that? What is the center picture here? What's that made up of? Anybody? What's in this pail? Don't everybody yell at once because I won't be able to hear you. we got aggregates and voids. VMA is an acronym, and we're going to refer to it all the time. You're going to see it in textbooks everywhere. Voids in mineral aggregate. Okay? It's these voids between the aggregates. Okay, that's your VMA. So if you look at your sketch, you can see that we have voids and we've got aggregate. If we add asphalt to it, we've got asphalt. You're also going to find out that some of this asphalt that you put into it gets absorbed by the aggregates, just like the water got absorbed in Portland cement concrete. Do you think the absorption value for aggregates absorbing asphalt cement, do you think it's greater or less than if it was absorbing water? Anybody? Hello? Less, right, Fabian? Based on viscosity. And we know that viscosity is going to change with temperature of your asphalt cement, okay? So we'll get into it. So just kind of keep these things in mind here. You're going to see this in one of the other units that I pulled it out of, but I just wanted to show it. So we got a representation of volumes in compacted asphalt. And we're also going to find out that you're going to add a total amount of asphalt cement. But the only effective asphalt cement is the one that coats the aggregates, because the rest gets absorbed. Okay? Any questions, Sophie? Okay. You're also going to have this, and this is uploaded for you, and during an exam or during a quiz, you're going to be calculating properties of an asphalt mix. Okay? But if you look at the picture here, and this is something that you always want to keep in mind, because you can solve the physical properties of asphalt pavement or asphalt mix using a schematic like this, a graphical representation, or formulas, and we'll get into the formulas later. There's numerous formulas that you'll be using to calculate air voids, VMA, okay, effective specific gravities, and so forth. Effective specific gravity of the aggregate, and away we go. So if we look at this schematic, this is the same thing that we just looked at the previous sketch. We've got air voids, okay, and we've got aggregates. And if you look here at the left, we've got asphalt cement, and we've got aggregates. And you can see that there's an overlap here of the asphalt cement, because it's indicating that some of this total asphalt is being absorbed by the aggregates, absorbed asphalt. And we have a legend. And these are the acronyms that we're going to be referring to, and that you see in most textbooks and in most articles, journals, papers, whatever the case may be. And we can see that if we look at volume on this side, and we can look at mass on this side, we're going to be going through some of these calculations. You'll understand that mass and the volume, sometimes the mass won't come into play. In other words, air voids. When we're doing mass calculations, it's not a problem because air doesn't weigh anything. But the volume. So we're looking at VMB. This is an intro, okay? This is volume. V stands for volume. M stands for mix. And B stands for basically asphalt cement. But we don't want to call it AC because we're referring to A as air voids. So bitumen. You've heard that many times, and that's again also referred to in many, many textbooks. So another name for asphalt cement is going to be bitumen. Okay, so if you hear the term bitumen, you know it's asphalt cement. Binder. It can also stand for binder. Okay, so this is the volume of the mix. This is bulk. Okay, Here we're looking at VB. This is the volume of the bitumen. Okay. So the mix, when we're talking about mix volume, we're talking about bulk. Just like bulk density, bulk volume. You're also going to have a term, and don't panic right now on learning these. They're all down here, but you're going to be using them later on. I just kind of want to go over this now so you can have an idea or an introduction. You're going to come up with a term with VMM. And you can see that it's less than your bulk. Okay, VMM stands for the voidless volume. If your asphalt cement had no voids, it would be at its maximum. Okay, so we've got volume of the mix maximum, VMM, voidless. There's no voids in it. So your volume is going to be less because you're not condensed it. Those air voids that you saw in that sketch are now reduced. They're eliminated. So the volume is going to decrease based on a certain amount of aggregate and based on a certain amount of asphalt cement, okay? VSB is the bulk aggregate. S stands for stone. VSE is the effective. It's the aggregate that doesn't absorb the asphalt cement. VB, volume of bitumen, volume of asphalt cement. And then you can see here that it's made up of the voids filled with asphalt, okay, or the effective. Get into this. So here's a sketch that we're going to be using. And on exams, I've had some students calculate all the physical properties just by using this chart. And some use the formulas. And we'll look at the formulas a little later. And again, this chart will be provided to you during an exam, so you can refer to it, plus the formulas. The formulas get pretty detailed, so obviously I've never memorized all of them, but they're available there. Any questions so far? Okay, so we're kind of looking at it. It's sort of the same type of matrix that Portland cement would have. You're going to have aggregate, you're going to have cement paste, and you're going to have air, pores, voids in concrete. For asphalt, it's very important. The aggregates, again, like Portland cement, are key. If your aggregates for asphalt cement are garbage, your mix is going to be garbage. It's not going to perform. We're going to be looking at the proportions of aggregate in an asphalt mix versus the proportions in the Portland cement mix. They're actually the opposite. Remember, we've always strived for more coarse aggregate in Portland cement concrete than fine aggregate. For asphalt, it's flipped around. You're going to have less coarse aggregate than you will have fine aggregate. It wasn't ideal to have crushed, sharp, angular particles for Portland cement concrete because it's a harsher mix. It would need more water for workability and more paste. So it didn't really contribute that much to compressive strength. Okay, it might have given you a little bit better bond between the aggregates and the cement paste, but it was a harsh mix. So it's not key to have sharp, angular, rough textured aggregate in Portland cement. However, for asphaltic pavement, concrete, you do. If you don't have sharp, rough, angular edges and aggregate in a hot mix, you're not going to have a stable mix. It's garbage. So again, now we're looking at a little bit different as compared to Portland cement. Okay. We know essentially the two ingredients, aggregates and asphalt cement. So let's look at the asphalt cement. Any questions so far? Okay. There's a fair amount of history, just like there is in the first use of Portland cements way back in the late 1800s. Same with the asphalt cements, the bitumens, the binders. Goes way back to the Greek days. There's a little bit of history on it. I'm not going to get into that because you can read that on your own. But there's definitions, various definitions of asphalt. Okay. It's a bituminous material, or bitumen materials, if you want to call it that. And they're made up of hydrocarbons. They're byproducts from the distillation, refining industries of crude oils. Here is a ASTM definition. Okay. Two types of bitumens or bituminous materials that are used in roadway construction. One, not so much anymore. The asphalt, okay, and the tars. Tars were originally used way back, but now that we can obtain asphalt cements from the refining industry or distillation process of crude oils, like I say, we draw different types of lubricants, we draw off different types of petroleum products, and then we're left with the sludge, the residue, bottom of the barrel, as they're sometimes referred to, because that's what it was. And that is asphalt cement. We can add certain solvents to it and make it better to our liking, and we'll get into that. So if you look at an ASTM definition, it's a black to dark brown solid or semi-solid cementitious material. We refer to it as cementitious because it is a cement, asphalt cement, which liquefies when heated. Okay, you know that. Your motor oil, if it's really, really stiff on a cold day, if you warm it up, okay, it's going to be less viscous. It's going to flow more. Okay, so we do the same with asphalt cements. When it's heated, they become more liquefied, which occur in a solid or semi-solid form in nature or obtained by refining petroleum. Wait a minute, it says here in nature. That's true. You may have heard of the asphalt cement lakes in Tobago, in Bermuda, Trinidad. They're actual natural deposits. Almost, if you want to consider, maybe like the tar sands, as they refer to it in Alberta. Mind you, it's mixed with sands, but as far as the lake deposits in Trinidad, they're actually lakes. Tar, we're not going to look into it because we don't use it anymore. Now that we can refine our crude oils, we can make and adjust the properties of the asphalt cements. This is just a little flow chart as to what happens. Don't worry about it. Just for your need. Okay. Asphalt cements. Before the advent of the petroleum industry, tars were the most common type of bitumen used in roadway construction. Okay, bitumen. In North America, asphalt cement is one of the refined byproducts from crude oil. And that's one of the things we do when we're refining crude oil for our fuels, gas, our diesel fuels, our naphthas, lubricants, oils for the industry. We're left with the residue. Asphalt cement can be obtained from two main sources. They occur naturally, and as we said, we're obtained by refining petroleum. This is just a little bit of statistics. This could change, obviously. We know that we use a lot of bitumen or asphalt cements in paving, roofing materials, your shingles, any asphaltic shingles that you use on your roof. Okay, obviously we use that. We use the crudes and we use it to make shingles. As a matter of fact, we're going to look at the City of Winnipeg specification now for asphalt cements and asphalt as we did for concrete, Portland cement. And now, as of I don't know how many years, a few years ago, you can city allows a certain amount of asphaltic shingles to be used in asphalt. Recyclable material. From rubber, your rubber tires, and they're shredded. Instead of going to the landfill, if you shred them small enough, way back in the early 1970s when I was still in the industry testing asphalt, we had an asphalt sample that we looked at. After we extracted the asphalt cement with it, we were left with aggregate. And I noticed in that clean aggregate, after we withdrew, as you guys that worked in the industry may say, as we did the burn off, well, back then we used trichloroethylene, we dissolved the asphalt cement, we're left with clean aggregate. There was little round rubberized pellets. The consultant failed to tell me at that time, when we sampled the asphalt, that it was a recycled mix. And in it, they had crumb rubber, keeping it out of the landfills. Why not use it? There's been some research done and even some applied research projects done in the past, your group as a matter of fact, where they used crumb rubber in Portland cement concrete, a certain percentage, before it became detrimental to the performance of the concrete. But if you can use a certain percent and it doesn't take away from the physical properties, why not use it? Why not bury some of it in the C base? Why not bury some of it in the A base? Done that. We've done that with colored glass. Okay, Highway 52, between Highway 59 and Steinbach. As you go through Mitchell, there's a section of pavement there when I was with highways that we actually buried 25% colored glass into the C base. Behaves excellent. Why not? Glass is one of the biggest culprits as far as trying to keep the environment clean because it doesn't decompose. So crush it, bury it in the C base. If it has no detrimental effects on it, why not? Okay. So same with this. So we're looking at various products. So asphalt shingles. Okay. Any questions so far? Virtually all the asphalt products used today are obtained from the refining of petroleum. Petroleum is processed to obtain gasoline, kerosene, fuel oils, lubricating oils, and I should have taken that out and I didn't. I hate the term et cetera, because what does it mean? Other oils, other lubricants. Okay. Any questions so far? 3 types of petroleum found in the Earth's crust. Not too worried about this right now here. Okay. So it's called fractional distillation. Okay, if you went to a refining plant, you'd see how they heat the crude, and at various temperatures, the byproducts are driven off or pulled off. So if you look at a fractional distillation process, and it works with heat and boiling. So between certain temperatures, between 40 and 95, you're going to get your gasoline coming off. Kerosenes need a little higher temperatures. So when you draw off all your products, your lubricating oils, your kerosene, your naphtha, your diesel oils, your gasoline, you're left with the residue. Okay, we're left with the junk. Bottom of the barrel, guck. Okay, don't use that term. It's residue. And it's asphalt. That's what it is. Take all these off, and we're left with that, and we find that it's got cementitious properties. This is just a chart that tells you the temperature rise, okay? So you can see here that at various temperatures, various hydrocarbons are pulled off. And as a matter of fact, some of these are going to be used with our asphalt. And we're going to call what's called cutbacks. We're going to be adding solvents. These are solvents, basically. Gasoline is a solvent, kerosene, it's a fuel, but it's also a solvent. Okay, we clean lots of stuff using gasoline. Great cleaner. Stinks like hell, but great cleaner. Kerosene, kerosene burners, heaters, diesel oil, diesel fuels. So we can actually use these solvent and add it to the asphalt cement, and we can change its viscosity, its properties. And then we make a product that we need for various applications in the road building industry. Okay? We'll come up to that as we go. Again, here's a little schematic of a refining, just taken out of the asphalt handbook. Okay. I had just mentioned something in the asphalt handbook. Stop here for a minute. I'm going to pull something up here now. Let's have a look. If you get a chance, this is the asphalt handbook. This is the one that I asked last year the students get, put out by the Asphalt Institute. It's the MS4 series. I have a copy of mine here, but this is it. I just took a picture of it. There's about 800 pages in this textbook. It covers everything from the cements to the aggregates, to the physical properties of aggregates, to the mix designs, whether you're going to use the super paved mix design method, partial mix design method, the Pavement Mix Design method, or the Hubbard, whatever. It covers maintenance, it covers design. So this handbook, the latest edition is the 7th edition. And unfortunately, the Asphalt Institute, I don't think if they gave you students discounts, they may. But if you were at Red River College, they have this one in the library. But I think last year, Ray, did you buy this book by any chance? Ray, can you hear me?
No, it did not.
No. Okay, it was the year after. See, I guess I specified last year to buy it, and this year because of the going online. But it is an excellent book, just like the CSA standard for concrete. This one here is also good. And most agencies, I mean, a lot of the DOT agencies in the States, they've adopted their design procedures, their construction. But a lot of them are originally based on the Asphalt Institute. And our next design that we'll be doing later on is a basis, the Asphalt Institute. So if you get a chance to get yourself a copy of this book, or if you see it in industry, by all means, and you can purchase it from the Asphalt Institute. It's about, I don't know, it's going to be about 180 bucks maybe. Sure. A little pricey, but well worth it. Okay, there it is. So we'll go back to, and this is taken out of that handbook. Okay, it's just a copy of it. Okay. We're going to get into a little bit of the specifics here. Asphalt cement, I'm going to try and go through a little quicker because there's a fair amount to cover. Okay. There's 3 broad phases, but it's a complex structure of carbon and hydrogen. That's essentially what it is. There's the asphaltenes, there's the resins, and then there's the oils. Okay. And they kind of give you an idea of ratio, but tells you what they all are. But as long as you know that the asphaltenes, resins, and oils. It's basically a complex structure. And we're not going to get into the chemistry of it. That's not what we're doing. Okay. Now, there's a couple of key properties of the asphalt cement that are very important when it comes to pavements. Okay. And that's ductility and adhesiveness. $120 on the website. Good. Okay, I'm way out to lunch then. It's not too bad, 120 bucks. Asphalt Institute. Nice. Okay. Good, thank you for that. Okay, so can anybody give me 1 or 2 words to describe ductility? What does ductility mean? Anybody? Ray, you're the expert. How would you describe ductility? Gold. Kind of like workability, yes. But if steel is ductile, what can you say if steel was ductile? Deform, right. Deformation, elongation. So those are key. The adhesiveness, obviously, how it's going to bind with the aggregates. Deformation, elongation, and its ductility. What's it like when we're talking about ductility? And then there's 2 other, or another key physical property that has a big bearing on the performance of pavement. It's the aging or hardening of these asphalt cements. We heat them up to a certain viscosity when we need to be able to place it and compact the asphalt pavements. But we know that with time, aging, it's a hardening. Okay? With aging, we get hardening out of the arteries. So, guys. So with aging, there's a hardening process. So now these physical properties of the asphalt cements change with time. With time, there's a hardening. And that's due to the evaporation and oxidation of the lighter, oily residue or constituents. You're mixing at high temperatures, and also due to oxidation of the oils to resins and resins to alphantines over a period of years. So those of you that I may have tested asphalt in the industry, you took a sample of hot mix asphalt, and let's say it sat in the field office for about 3 weeks before you even got around to sending it to the lab real quickly. That hardened asphalt in a bag or in a pail or whatever sample container you use went to the lab. They're going to test it out. Now they're going to heat it up. So they're reheating it again. Every time you're reheating hot mix asphaltic concrete, you're burning off volatiles. Okay, so you're changing the properties of that asphalt cement. Aging or hardening of asphalt is due to the evaporation and oxidation of the lighter oily constituents during mixing at high temperatures. Now, obviously, there's going to be a certain mixing temperature at the plant. And when you bring it into the lab, hopefully you don't exceed those temperatures. You may want to really crank the heat up to speed up the process. You can't do that. And if you have to keep reheating it, keep reheating it, keep reheating it for your various tests, it doesn't do it any good. It drives up your stability and increases stability, but you get a false reading. Okay, so we've got an aging and hardening process. So the ductility is going to change. Some of the adhesiveness is going to change. We can classify paving asphalts. It's like Portland cements. You've got 6 different types here in Canada. You're going to have different asphalt cement grades or viscosities. And you're going to classify them. Basically, the 2 methods that they were classifying is based on viscosity or penetration. Penetration was derived from testing the asphalt to determine how soft that asphalt cement is at a certain temperature. You would penetrate it with a needle. Originally, they used a sewing machine needle. Okay. Asphalt cements are available in different grades. The grades of the asphalt cement and the temperatures at which they can be used efficiently, effectively, is based on its viscosity. Okay. I think I'm going to ask you guys viscosity. If your viscosity is high, is your asphalt cement harder or softer? If you have a high viscosity, is it more? It's sorry?
Would that make it softer that it could flow better?
No.
Harder?
Harder. See, a lot of people think that a high viscosity means more fluid. It doesn't. Okay. And it's a common error. Most people, yeah, it's thicker. Yeah. Viscosity of asphalt cements changes with temperature. It ranges from a solid, thick, higher viscosity to a fairly thin liquid, lower viscosity. Asphalt cements will have a lower viscosity, more fluid-like at high temperatures. Okay, so that's something that a lot of people get versed. Okay, higher viscosity means harder. Lower viscosity means more fluid. Because viscosity is defined as the resistance to flow by gravity. The resistance. One is actually by gravity, and one would be by imposed loadings. There's 2 different types of viscosities. We're looking at dynamic viscosities as one. 5W30 summer versus OW30 winter. Exactly. Okay. So in wintertime, your viscosity is higher, not lower. Right. Okay. So just kind of keep that in mind. It's easy to get those two mixed up. I know I've done it a few times. Okay. Asphalt cements behave also on the time of loading. Interesting. How many of you guys have parked the vehicle on a hot summer day on the asphalt pavement, and then when you pull away, you'll see a slight indentation or a slight marking? And that's in your car. And yet that same pavement that you're parked on, got semi-trailers loaded to the hilt going by and there's no deflection. One is sustained, loading, one isn't. Sustained loading is going to give you more of the deformation later on. Under sustained loads, example, slow-moving trucks, asphalt cement act like viscous liquids and flow. If you're parked. If you're going really fast, you're not going to get it. So that's why many times when you're actually paving sections of the highway and you park, you're an inspector, you come up and you park on it, superintendent would say, move your car off onto the shoulder, get it off the pavement, because you parked it. It's still hot. But mat is still hot. Still, you've got sustained loading. Very slow, or you're standing. You're going to imprint that pavement. Any questions so far? Okay. This just kind of gives you a microscopic view of the flow characteristics. So now we're going to look at the properties that were important, was ductility and adhesiveness. Now we're going to look at the grading and how we classify it. So remember, we said we can classify our asphalt cements into various grades, viscosities, and we got penetration. And there's two types of viscosities that we look at. We look at the dynamic, the absolute viscosity is also referred to as dynamic, or the kinematic viscosity. And there's a difference. And then we also look at penetration, and that'll give us a degree of softness or hardness by penetration versus viscosity. Okay. They both are used to characterize, and there is some form of correlation between penetration and viscosity, but we don't try and memorize those. We can make a chart of viscosities, we can make a chart of penetration, and we can see a correlation between them. But one is a penetration, one is a viscosity test. Okay? Dynamic viscosity, we refer to it as poises. That's how we measure it. Here's the difference. Dynamic or absolute, same thing, just a different term, is a measure of the resistance of fluid to flow under external force. Okay, you've applied a force to it. You're rolling the asphalt, whatever the case may be. Okay, so it's measuring the resistance to that flow by that external force. Whereas kinematic, okay, it's also a measure of resistance, but it's under the force of gravity, just by itself. Okay, kinematic viscosity of a liquid is equal to the absolute viscosity, and you divide that by the density of the asphalt. Now, asphalt cement is a little over 1. And we're going to note that in most of your calculations and with most of the asphalt cements that we use, you've got a specific gravity of about 1.03, 1.029 in that range. It's slightly more than water because it doesn't float on water. Your oils may float on water, but the asphalt cement's got other constituent products in it that makes it heavier, but it's close. 1.029 sort of is an average, 1.03, again, depending on possibly the asphalt cement that you're working with, the viscosity. Okay, so dynamic and kinematic. And we look at these viscosities to temperatures when we're actually heating the asphalt cements at the batch plant. We're going to liquefy it. You're going to stick it into the kiln where the aggregates are being heated, and you're going to mix the hot asphalt cements with the hot aggregates. Then you're going to deliver it to the job site. So there's various temperatures for mixing, and then there's going to be various temperatures that you need for placement and compaction. Note the absolute viscosity of a liquid measured in poises and its kinematic viscosity measured in Stokes have approximately the same value. Okay? Viscosity after aging is also used to grade asphalt cements. Okay? These are the two main definitions, dynamic and kinematic. Okay? We want to know what those viscosities are so we can grade our different asphalt cements. And there's numerous ones out there. This just tells you how they do it. Don't worry about it. It's a test procedure. Ask you to memorize these test procedures. And so we said that viscosity was one way to grade the asphalts, the penetration. And this is one of the tests that you're going to have to know why this test is done. You don't have to know the procedures. We would if we were doing a lab, and we're not doing this lab in the physical, in the virtual labs. We do it during the physical lab. This one here, it's a form of grading the asphalt cements. And you have different values. You can have what's called a 100, 200 penetration grade asphalt. You can have a 200, 300 penetration grade asphalt. The city kind of goes in between with the MI, and they have a 150, 200. So now they're sort of blending, and we'll get into that a little bit more. Essentially, it was a test derived as to how far a needle penetrates the asphalt cement at a certain temperature with a certain amount of mass on that needle, pushing it in over a certain time. And that would be the penetration test. And that's how it was graded. So it's an empirical test. Okay? The depth a needle with 100 grams total mass penetrates into a prepared asphalt sample in 5 seconds is the penetration value of the sample. And that's what it's referred to. So if you looked at this little sketch, you've got asphalt cement at 25 degrees Celsius. Bring your needle down, it's 100 grams. You let it fall into the heated asphalt cement, and it's going to penetrate. And the number of millimeters it penetrates is recorded. It's recorded in tenths of a millimeter. So when you talk about a penetration of 98, that's 98 1/10. So that needle actually penetrated 9.8 millimeters. But we refer to it as a penetration value of 98. Okay. If it was 150, 150, one of the penetration grades are 200. So let's take 200, 10 grade asphalt cement. That means penetration on virgin asphalt cement without aging or hardening would be 20 millimeters. Okay, it's 1/10. So remember that. These come up quite a bit in true or false questions. You can relate this many, many ways. So understand that penetration value, okay, it's the amount the needle penetrates, and you record it in tenths of a millimeter. Any question on that? Okay. So again, we talked about the grading based on viscosity or penetration. And there's various grades, and I'm not going to ask you to memorize these because there's no need to. But you can see here that the viscosity ones, we'll call it asphalt cement 2.5, 5, 10, 20. And it gives you the various physical properties of these asphalt cements that are graded based on viscosity. And here you can see, for example, an AC 2.5, okay, with a viscosity of 250 plus or minus 50. AC 5 is 500. AC 10 is 1,000. So that tells you right away that this would be 250, 500, 1,000, 2,000. And if you look at the penetrations, every asphalt cement that is, say, graded or classified under viscosity has a penetration value approximate. And here it is, 200, 120, 70, and 40, and 20. So you might want to correlate it. there's a flash point that we're going to look at later on. Solubility. So there's various tests that you have to run on these asphalt cements from a quality control point of view, no different than what you would run on your Portland cements. You know, the fineness, loss of ignition, the soundness, strength of the asphalt cement. Okay, Portland cement. Same with here. They have various properties. Flash point. At what temperature can that asphalt cement be safely heated before it ignites? There's an open flame. We know that if we got extreme temperatures, we have to know at what temperature is that asphalt cement going to actually light up and start to burn. It's very important. We'll get into that a little bit more later. Any questions? Our specifications have changed now. You've heard of the Super Pave, and more and more agencies are going to it. And the Super Pave program actually had a way of classifying asphalt cements based on performance. So they call them PGs, performance grade, not penetration grade. We try and use the term pen grade for short, because PG stands for performance grade. So it's totally different than the penetration. Why did we do it? Well, there's limitations on the current system of grading before Super Pave came in. Viscosity tests measure only the viscous component of asphalt cements. They do not measure the elastic properties. Okay. In general, tests are performed on unaged or tank binder. You've got an asphalt cement sample submitted to you from the refinery, and viscosity tests on it and pen grade tests. But that is what they call tank binder from the storage tank. It hasn't been put to service. The aging and the hardening is going to have a big bearing on it. And that's what happens in the actual real world. With aging, our performance of that mix is going to be based on properties of that asphalt cement, and it changes with time. Current specification testing temperatures do not cover the full range of pavement service temperatures. Okay, that's key. You test that asphalt cement when it's submitted, call it virgin asphalt cements, but our pavements, the performance of our pavements, okay, are going to be a result of the changes of that asphalt cement with service life and time and temperatures. It just kind of gives you an idea what I'm going to. A couple of key points here, though, at high temperatures. This is now we're going to just look at the asphalt cements and how they behave. If the asphalt cement deforms and does not return to its original dimension, it's called plastic. Plastic flow of asphalt cements is one of the key factors of pavement rutting. And you've seen pavement rutting, eh? When you're driving down the highway, especially at areas where there's lots of stress, at traffic lights or at stop signs, and depending, one of the worst areas was on the west perimeter, just as you're approaching McGilvery, okay, from the south, you had ruts, the impressions of the wheels. In other words, the asphalt cement was mounded up between the wheels. It's rutted. And that's due to a couple of factors, but one of the key is that it's in plastic. So we have various products. So at high temperatures, you know that. Well, it's in a plastic state. At intermediate temperatures, more of a viscoelastic, if you want to call it. Okay. At low temperatures, or when subjected to rapidly applied loads, okay, fast-moving trucks, asphalt cement behaves as an elastic. It deforms under loading, and when it unloaded, it returns back to its original shape. So plastic, it does not. Elastic, it does. That's what you want. You want it to return back to its shape. Make sense? So these are all the things you have to consider when you're going to be designing an asphalt pavement. And some of the old methods that we've had, are sort of gone by the wayside. We still here in Winnipeg and Manitoba, the province, use Marshall designs of performance grade, penetration graded asphalt. Now I know MI is moving to the Marshall method of design, but using performance grade asphalt cements. So in other words, they're using performance grade to grade the asphalt under that, and we'll see why. Whereas the penetration and the viscosity, the old way, didn't take into consideration the surface temperatures of that pavement, whereas the performance grade will. It's going to look at the minimum and maximum temperatures that those pavements can undergo. Okay, we may use a 150, 200 pen grade in Winnipeg, and you're up at Thompson, Manitoba, and you're still using a 150, 200 pen grade asphalt. Well, the service temperatures in Thompson or in Churchill throughout the year are totally different than in Winnipeg, or even Grand Forks. You got to take that into consideration, the service life of your pavements. And what we've got here is they've got a classification, and how they rate that. I'm not too worried about this 20 millimeters below the surface, but what I'm trying to get to you is when you see this designation, and there's various, a PG 6422, for example, what does that really mean? Okay, well, PG, performance grade, straightforward. 64 and minus 22, what are they? Well, it's the average 7-day maximum pavement design temperature, 7-day maximum pavement design temperature, and minus 22 is the minimum 1-day minimum temperature. So in other words, you're designing a pavement using an asphalt cement that has the capabilities of 64 to minus 22. Now, 64 is not that high, but it's an average. So now when you're in Thompson, you might say, okay, my PG 6422 may not work because the average 7-day maximum in Thompson may be a lot less. Maybe it's only 50, just guessing, but okay. So that's what it means. So you may be asked on a test, what does PG 6422 stand for? What does PG 80, 30, minus 30 stand for? That negative, that's a negative. That's not 64 to 22. It's 64 minus 22. Those are temperatures, okay? And that's how it's rated, performance grades. Whereas you see penetration is different. Questions? This just kind of gives you a comparison between the various type under AASHTO, binder specification. Okay. Got to get into the lab here right away. There's a fair amount here I'd like to cover. Let me just see. I'm going to go through there. Just getting into cutbacks. Maybe I can make up for this even the next week. Okay, let's just look at it for a few minutes here. We'll take a break, and then at 2:30 we'll come back and we'll do the lab. But this is what we'll at least cover the cutbacks. Remember, I said, okay, we've got asphalt cements and they have certain properties. Maybe we can't readily use them. Viscosity might not be there for the type of pavements. So we can liquefy. We can change the viscosity. One way is doing it is by heating it, obviously, but that's only going to help during the temperature increases. So we want to cut them. In other words, we want to change the viscosity so that temperature may not have so much of a bearing on it. If your oil was too thick, your cake batter is too thick, what do? You add water, changing its viscosity. Well, here, because we're working with asphalt cements, adding water is one way when we're making emulsions, and we'll talk about that. But the other way is taking those solvents that we let off during the refining, take some of that gasoline, take some of that kerosene, take some of that naphtha, and mix it with your asphalt cements and you change their viscosity. They're easier to work with at certain temperatures and certain conditions. So it's called liquefying asphalt cements or cutbacks. We're cutting back the viscosity. And one of the ingredients that we use for cutting asphalt is you see it sometimes used, well, maybe not so anymore because they're really stringent on that, but in the past, a lot of the trucks delivering hot asphalt would coat their trucks with diesel fuel, the back of them, so the asphalt will slide out. Well, if you're using diesel fuel, excuse me, change the viscosity of your asphalt cement, if you're coating your box, that's going to change your mix. That's a no-no. So you would, again, if you ever saw that on the job site, you would tell the contractor, you cannot use diesel fuel to coat your truck box so the asphalt slides out easier, because if you got that diesel fuel into your asphalt, it will start dissolving it. How many of you guys fill up your own gas in your car? Not everybody, right? What do they have around the pump islands? Okay, you pull up at the gas pumps. Pull into the parking lot, asphaltic parking lot. But right around the pump islands, where your gas pumps are, is it asphalt? Or is it a concrete slab? Anybody? Concrete. Because a lot of people filling their cars overflow. Gas starts running down the side of your car onto the ground. Well, that asphaltic parking lot was paved right up to the pump islands. So now your car is parked on asphalt. Can you imagine what that asphalt pavement would look like at the end of a day, at the end of a week, at the end of a month? They'd always be repairing it. So they use the concrete, Portland cement concrete. So now we know that the effects of gasoline on asphalt. So we can actually use this gasoline to our advantage when we want to liquefy our asphalt cements under certain controlled conditions. So cutback asphalts are produced by dissolving asphalt cement with solvents, petroleum distillate, to reduce its viscosity. And thus cutback asphalts are easier to use at ordinary temperatures. Okay? At high temperatures, we don't need to, because we can heat that asphalt up, asphalt cement to a certain temperature, not a problem. But at ordinary temperatures, we want to be able to work with it. We want to be able to work it. It's like Portland cement concrete. If you can't work with it because it's too stiff, what good is it? Same with this. You got to be able to place it, compact it. Okay, so we got what's called cutbacks. And we've got three types: rapid curing, medium curing, and slow curing. And it's pretty straightforward. RC, MC, SC. So when we want a rapid curing, we cut it with naphtha or gasoline, right? For rapid cure. So that you kind of give your percentage of volatiles when it's most fluid and when it's most viscous. Okay, so 30 to 50% volatiles is when it's most fluid. Medium curing, now we use kerosene. So these are highlighted because these are important. Which solvent do you use to produce RC? Which one do you use to produce MC? Which one do you use for slow C? SC, okay? So naphtha or gasoline, kerosene, and diesel. You can actually make an SC directly from the distillation process, but also just take the asphalt cements and cut it with diesel fuel and you'll make a slow cure. And these you'll see many times are being used for prime coats, tack coats. Place it on your granular base, or your asphalt pavement, adhere to it. Okay, so those are the three cutbacks: rapid cure, medium cure, slow cure, and we're using solvents. Now, there's also what we call emulsified asphalts. And an emulsion is basically water-based, right? Emulsifiers. So you can have emulsifiers, you can have water. And that's exactly what it is. Emulsified asphalt is produced by combining asphalt cement with water and an emulsifying agent. Then you're going to use that emulsifier to break it down. You want to change the viscosity. Now, there's some advantages to using emulsified asphalt versus rapid cure. There's what we call flash points, or the breaking time. At certain time after we place this asphalt cement, the solvents will flash off. Okay? The volatiles evaporate, and you're left with that product. You're using it to place it, to be able to work it, but after a while it'll evaporate. It'll flash off. And there's a time for that. And that time is noted as when the asphalt actually changes back to a viscous. So if we're using emulsified asphalts, which ones would you rather be standing beside all day long? Okay, you're laying down tack coat, or you're laying down prime coat. Would you rather use an emulsified asphalt, or would you rather use one of these rapid cures, medium cures, or slow cure? Anybody? Why, Margot? Go ahead, you can open your mic.
Because it's not as toxic or as smelly.
You got it right. Exactly that, Margot. It's if you were on a paving crew and when those solvents flash gasoline after a while, you hang around it too long, you'll get headaches because it's flashing off. Well, emulsified asphalts are basically water-based and soap-based. They're not going to harm you. They are more environmentally friendly. So there is a push now. Plus, what happens if you heat solvents up to such extreme temperatures? What's the chance of happening? Ignition.
Fire?
Exactly. So we're coming up to that. There's three main reasons why emulsified asphalts are more superior. One is the environmental toxicity, okay, more environmentally friendly. One is that there's less chance of ignition. In fact, it eliminates ignition due to an open flame or a spark off of a truck or machinery. And the other one is if they're emulsified, they're water-based, your aggregates don't have to be bone dry. They can be damp, they can be cool. So working with emulsified asphalt, cements, make a lot more sense. But we'd still use both. Yeah, thanks, Margot. Very good. Yeah. So they just talk to you about the percentages, but the emulsifying agent breaks up the asphalt cements and disperses it into a form of very fine droplets. That's essentially what we're doing. We're trying to change its viscosity. Don't worry about the cationic, anionic, and so forth. But this is important. The time that is required for the water to evaporate, the asphalt particles to recombine from a continuous film of asphalt is called the setting time or breaking time. And any of you guys that have worked on an asphalt paving job, you'll see them laying tack coat down. Okay, they're going to be paving the asphalt cement. They got a distributor truck with spray bars on the back, and he rolls out a layer of tack coat. Essentially, it could be a cutback. It could be an emulsifying agent, an emulsified asphalt. So you got to give it some time to break or set up. And what that happens is whether it's an emulsified asphalt, that water and emulsifying agent evaporates, or it's a cutback and those solvents flash off. Then the pavement goes on it. You don't want to have the pavement go over wet emulsified asphalt or cutbacks. It's got to flash off and just become tacky. You're creating a glue, if you want to call it, adhesiveness. The different emulsifying asphalt products with fast RS, medium S, and slow breaking times make emulsified asphalt suitable for a wide variety of pavements. So now we're talking about rapid setting, medium setting, and slow setting. You might have heard of SS1. That is one of the main pack coats that is used by the province, even the city of Winnipeg. We'll see a lot of specs. We'll talk. It's SS1. Okay, slow setting time, emulsified asphalt. You don't want it to break too fast. But so now the contractor's got to stage his work in such a way that it's going to flash off right at the right time and he can come up to it. And those setting times, or breaking times as they're referred to, is based on the quantity and type of emulsifier used and the amount, the relative proportion of water and asphalt cement. It's highlighted because I like yellow. It's the only reason I highlight, because I like the color yellow. And then here's the grades of emulsifier. Okay, rapid setting, medium setting, slow setting. And to see if you saw that just tells you whether it's cationic or emulsified type. And here's the 3 ingredients, and we're going to take a break here right away. We'll have to try and finish off this next week. Excuse me, I'll try and bring that up with the aggregates. Pardon me. Advantages of using emulsified asphalt. They can be used either with cold or hot aggregates. Perfect, eh? They can be used with aggregate that is dry, damp, or wet. Perfect, yeah. And it eliminates the fire, toxicity hazards, and the environmental pollution cutback. And even when you're not using these cutbacks, just the working on an asphalt paving crew all day long, just the hot asphalt. You'll see in the summertime, it's a heck of a job to work on. But in the fall, October, November, if you're lucky to pave that late, you'll see that most of those workers on a cold October day, they huddle close to the mat because the temperature coming off a hot asphalt mat, you can feel it. It's a bugger in 30-degree weather during July, but it's a blessing. October, different than built up hot applied roofs. Why doesn't the paving crew like using it, Clive? You talking about emulsifieds? I've got a question here. Go ahead, Clive. Let everybody know. Okay, harder to work. Are you talking about the emulsified asphalts? Really? They like it when it's nice and flowable. Where did you end up using it? Was it for like a tack coat, or were you actually mixing asphaltic concrete, asphaltic pavement material with the emulsifier, PTH 75? And was that the asphalt, or was that the tack coat or prime coat? Asphalt, really? You don't like it, eh? Too slow? Harder to work with, eh? Yeah, well. Oh well. Contractors are usually the first to whine. Goes too quickly. Well, yes, and that's where the production and your work has to be planned out in such a way that when you get that asphalt, you can place it, pack it quickly. But you know, if you're going to be doing a lot of this work in residential areas, if that ever happens, I mean, highways may not be so much the case. But if you're going through an area where there's the environmental concerns, or the people don't like the stink or the smell, whatever you want to call it, they may be forced to. But true, if it cools too quickly, you got to know what you're doing. You got to be able to get it down and compact it before it sets up too quickly. Good. Okay. So there's additives sometimes we can add. One of the main agents, and I'm going to highlight this, and you guys can do it on your own. Okay. Come on. Anti-stripping additives. Lime is one of the key anti-stripping agents. Does anybody know what we're talking about? An anti-stripping additive. We'll look at this when we're looking into aggregates. But what is stripping? And that's quite common when you're going to use recycled asphalts and you want to blend them with virgin asphalts. Okay, you're going to have a virgin mix, and then you're going to take recycled pavements that have been ground down, heat them up, and you're going to mix them, maybe 75-25 or maybe 80-20. So now you're actually using recycled pavements. Well, if you're using recycled pavements, the asphalt cements in these recycled pavements are old and aged and hardened. And some of the things that contribute to this, and this can also happen with the new virgin asphalt, is the aggregates. They're either hydrophobic or hydrophilic. And the aggregates that are very love water, in other words, okay? They take on the water quickly. You're going to strip some of that asphalt cement off the aggregates. So we know lime can be used to dry up subgrade soils. If you're compacting, you're building a road and it's rained for a week, the contractor wants to get on, but he can't because the subgrades are too wet. Many times he can use 1-2% lime and he'll dry up that clay subgrade so he can at least compact it. It's changing the moisture content. Lime is a good anti-stripping agent, and it prevents you're trying to dry it up. In other words, you don't want the water to strip the asphalt cement off the aggregates. So that's what it means as an anti-stripping agent. Okay, so it's aggregates that are very prone to water. They love water. Okay. And there's your prime or tack coat SS1 that is quite commonly used in Winnipeg. So these are some of the uses you can use it. Okay, rapid settings, but the main ones I highlighted here are the ones that we typically use for prime and tacks. Okay, base stabilization. Many times if you've got inferior base material aggregates industry, well, Winnipeg here is different. We have good aggregates. But you might be in some areas where you can actually add SS1 and pulvey it into the if you had to say a real fine sand subgrade, wanted to stabilize it, base stabilization. Instead of adding cements or fly ash, you can also add SS1s to it. Okay. We're almost done here. I'm going to quickly go over this, and then we'll pick up on the lab. Okay, there are tests that you do for asphalt cement that do similar to what we did for Portland cements. You don't have to know the procedures of each test, but know what the tests are and why we do them. Penetration measures the consistency or hardness. Okay, there's a penetration test. Viscosity represents the maximum temperature the asphalt pavement is likely to experience. Okay, viscosity, maximum temperature. Kinematic is the temperature chosen to represent the mixing temperatures at the plant. Okay, we got to mix asphalt cement with hot aggregates to get a hot HMAC. So that 135 is the temperature that asphalt typically is heated at the plant. Okay, so we're simulating that and we're checking the viscosity. Flash point is the temperature at which asphalt cements may be safely heated without danger of instantaneous flash. There's an open flame. If there's no open flame, you should be okay, but you never know. Spark, somebody hits the tailgate of their truck or whatever. So it's that temperature, flash point, okay? Thin film oven tests. And there's the rolling thin film oven test, which is just a different procedure, but essentially the same test. For short-term aging, it's to simulate the heating that occurs at the plant, okay? Designed to measure the changes of the penetration value or viscosity for short-term aging at the plant. Okay? This is essentially the same thing, but it's quicker to run. The other one takes, I think, a couple of hours, not mistaken, up a period of 5 hours. This one you can do in something like 85 minutes. So this is the 6. Then there's the ductility test that measures the elongation. Solubility test. We're using carbon disulfide to see what kind of impurities we're going to have in it. Dissolve the asphalt cement, we're left with impurities. So we can determine what the content is. And then the water and asphalt cement test. We know the water sometimes gets trapped in with the asphalt cement. Okay, so those are the 9 tests. Know them, just finish this. Know those 9 tests and why we do them, but you don't have to know the procedures of how to run the test. That's not what we're here for, okay? Just like there were certain tests, the 6 tests that the cement manufacturer had to do for Portland cement concrete, there's various ones here for quality control to ensure that the asphalt cement that you're selling from out to west, whether it's Husky or whether it's Esso, any of the other major oil producers. Any questions? Okay, let's take a 10, 15-minute break. It's 2:25. I want to go over the lab, and this lab will be aggregate blending, just like we blended concrete aggregate. This is going to be a little more fun because now you're going to be blending 4 types of aggregates instead of just 2. So let's come back at 2:35. Is that okay? I'll stop the recording, but I'll just leave everything as is, and then hopefully we can go through that lab quicker because you've already are experts on blending. Any questions on the asphalt cement? I had to go through quickly, guys. We're down to the nitty-gritty here. We've got a fair amount to cover, and hopefully next year we don't have to go to these 12 weeks. 24-week course can stay at 24 weeks. So those of you that just want to take in that 24 weeks, just don't graduate this year, and you can come back and you'll have it in 24 weeks. Fair game? Okay. You guys are 2:35. I'm back. Okay. Everybody back? Ready to go? Let's try and wrap this up. Okay. Essentially, the labs that we'll be doing in this section is all pertaining to the asphalt mix design. Just like we designed a concrete mix, we're designing an asphaltic mix. I want to ensure that it meets the City of Winnipeg specifications, and that's what we're looking at. We're looking at the City of Winnipeg. We could be looking at MI, but they do theirs a little differently. We're designing an asphalt mix. You can design the amount of AC, asphalt cement, based on as a percent of total aggregate. You can also design it as AC as a percent of total mix. So in other words, that's percent of total mix, which is the asphalt cement plus the aggregates. And the Asphalt Institute looks at it that way, and as does the City of Winnipeg and most agencies. Excuse me. Both are acceptable. You have to know how the mix design is based on, because if you're calibrating the plant, and you're saying you're going to be using 5.3% AC, is that 5.3% AC based on the aggregate, or 5.3% based on total mix? That's going to affect the amount of AC you need to put into your mix with the aggregate. So it's important. So we're going to follow the City of Winnipeg, and we're going to look at their specifications first before we get into the blend here. So I'm up and recording again. I'm going to pull up City of Winnipeg specifications. I believe you have that already uploaded in one. If not, we can find it. It's not a problem. It's the standard construction specifications, and you're going to go into it. So I'll pull it up here, and we'll see it here right away. Okay, 3410 R12. The other one was 3310, I believe. So this is the pavement works. Okay. So what's highlighted here, the city did this. This is when they have a revision to their spec. And here you can see that the last time it was written was 2015, 6 years ago. It's a revision 12. Again, it's like any other specifications. There's physical properties that your constituents have to meet, just like there is for reinforcing, admixtures, cement, aggregates, and so forth. Okay. So we're going to move into here, and they have a pretty extensive talk about aggregates. They talk about fine aggregates and coarse aggregates. There's various tests that you have to run on the aggregates to ensure that it meets the city requirements, the soundness, the abrasion, crushed aggregate. And this is a test that I think you guys did last year with Natalie in her GM1. She'd have you do crush count on A base. It's essentially the same way, except now you're looking for 2 fractured faces. And that's very important in asphalt. They have certain tests on their AC, as we were referring to. There's the viscosity chart. There's the viscosity chart that the AC has to meet. And here's the revision, okay? Blending of recycled asphalt shingles shall be during the production of the asphalt, and that the mix produced shall consist of a uniform blend of all materials. It basically has to be shredded, has to be cut up quite fine. A mix design statement, again, very similar to what's a concrete. What are the physical properties? This is kind of important. You're going to have aggregate requirements, and they have various asphaltic types that they place in the city of Winnipeg. Most of it is type 1A. However, they can go to surface courses, and we'll look at that right away. But here again, once you determine the blend, once you determine this is the gradation that the asphalt has to be mixed at, this 6.3.1 gives you the plus and minus tolerance from that gradation. You're going to have a wide envelope at first, and your mix design has to meet in there. And once it's in there, and you say based on a blend of 50-50, 25-25, this is the grading. Now it's plus or minus from that grading. So now your envelope has become that much narrower. So you can see that down here, passing the 80 plus or minus 2. Now I want to bring your attention to something. The city of Winnipeg, I think, are a little bit, I wouldn't say backwards. And that is, they are using the Canadian metric sieve size for just about all their materials, which is not right. Canadian metric sieve size have been set up for concrete. Now, it's a gradation. They can use it. It's not a problem. But when they're using these Canadian metric sieve size, and then you're doing a test following ASTM, ASTM refers to the sieve sizes ASTM metric, not a 5 millimeter, 4.75, not a 2.5, 2.36. So if you were doing a crush count, like Natalie had you do a crush count, and you were using it from the sieve analysis. So as you're doing your sieve analysis, you just said, I'm going to keep everything 4.75 and above separate. And then later on, I'm going to go and I'm going to pull out crushed and uncrushed. So you did a sieve using the Canadian metric sieves. You're saving everything on the 5 millimeter and above. Now you got to take it and screen it over a 4.75. Handling it twice. They don't recognize that. Because if you read the other tests that are required for asphalt, they fall under ASTM. I've mentioned to the independent labs to tell the city to smarten up. Anyways, so that's sort of the test procedures, sieve analysis that we're looking at. We're going to be looking under ASTM. When you're plotting a gradation, you can do the sieve using your ASTM metric. But for your grading envelope, use the Canadian metric. Doesn't matter, the curve's still going to fall in between. Instead of now, percent passing 4.75 is going to be very close to the 5 millimeter when you plot it. Envelope will be back a bit. Have a look at that. Okay? So these are the physical requirements. They're talking about the recycled asphalt shingles. Okay, I'm going to go to this, but I got to turn this around because it's this is the one that pertains to the different mixes. You can see here they're using Canadian metric again, which they shouldn't, but so they got a type 1A surface course mix, type 1 surface course, type 2, type 3. And you can see that they're based basically on top size, maximum nominal size, maximum size. You can see that this base course would be for thicker sections of asphalt, because you're going up to as far as a 1 inch material. Okay. 25 millimeters, 90 to 100. You can actually have 10% retained on the 25 millimeter. Whereas we're using type 1A surface course. And that's because we do a lot of asphaltic overlays where we mill off the existing asphalt pavement and we put on a new lift of hot mix. So now most of them are type 1A because they're only looking at about 60 millimeters, 65 millimeters of total thickness. And your mat, again, is based on the maximum nominal size, 3.5 to 4 times that. Okay. And here they're talking about crush count minimum. 2 fractured faces. I can't remember with Natalie when you guys were doing, was it 1 fractured face or 2? I can't remember, but for asphalt aggregate, sorry, asphalt aggregates should be 2 fractured faces. And here's the other properties now that your mix design has to meet. The percentage, asphalt cement, percent of total sample weight or mass, 5 to 6. Voids in mineral aggregate, remember we looked at that on our chart, the VMA, minimum 14. Percent air voids, you want 3-5% by volume. The Marshall stability. We talked about compression strength tests for concrete and asphalt pavements. We talk about stability because it's an interlocking. We load the briquettes, so it's a cylinder. But instead of loading it this way, turn it in a braking head and you load it this way. Okay, so you're going to be loading it this way. And flow is the amount of deformation at maximum stability. So those are the key tests that you're going to be doing. You're going to also determine the maximum density, but that is going to be a function of the mix. There's no spec for it. It is what it is. Design and mix to meet all the other properties. Density is going to be what it's going to be. Okay? So here we're looking at the type 1A. This one here. This is what we're designing. And you can find this specification under City of Winnipeg website, Standard Construction Specifications, and it's under Surface Works, and it's 3410. Okay? Any questions so far? There's money. Okay. Let me go back and read. Okay. And it gets into the actual base preparation and so forth. For now, we're just wanting to bring you the sieve analysis. So you could see that there was a sieve analysis. The grading limits given for type 1A surface course. What I'm going to do now is I'm going to turn to an example that we used a few years back. Had we had this lab physically, you would have had 4 aggregates to sieve and determine the gradation. And as I mentioned in the lab on Learn, it's donated from Maple Leaf Construction. The coarse 16 millimeter crushed limestone aggregate is from their Stonewall quarry, as is the crushed chips or crushed fines. We refer to them as chips many times, and I'll try not to, but sometimes I will call it chips, but it's because it's bled off when they're crushing the coarse. When they're producing the coarse 16 millimeter crushed limestone, and we call it 16 because that is the top size for a type 1A mix. They will take the fines off and the crushed fines. The natural fines comes from Birds Hill. They're what they call Pit 63 on Garvin Road. That's in the Birds Hill area. And then the VMA sand. Now, there's no such thing as VMA sand. We call it VMA sand because it is a finer sand that controls the amount of VMA in your mix. So we just call it a VMA sand. But if you look at the grading, you'll find that it's very, very fine. It has to be very, very fine, but it's finer than their natural sand. So in essence, we have 1 coarse aggregate and we have 3 fine aggregates. We've got the crushed fines, sometimes referred to as 6 millimeters. We have the natural fines, fine aggregate, but it's natural deposits. They may just screen out the coarse. So it's essentially 100% passing the 4.75, and then they'll look for that VMA sand, and that's what controls the VMAs, the air voids. Any questions? Okay, it's quite a mouthful. Anyhow, let's just go over to the spreadsheet I got going here. And this is an example. Your data values are going to be totally different. I pulled this off from a couple of years ago, so it has changed. So what I've done here, you can see I've put it together. This is back 2017, 2018. Okay, oh, you guys can't see that. Hold on a minute. Okay, now you should see it now coming up. Okay. Everybody see it. Okay, so you can see here we got 4 types of aggregates. I did a spreadsheet like this. I like to use Excel. There is a procedure that we're going to be look at that you can use mathematical equations to determine the percentages for, say, 3 aggregates. And there's an exercise in the assignment based on 3 aggregates. I haven't figured this one out for 4 aggregates. There's got to be a way of doing it, but typically, because of Excel spreadsheets now, we can go trial and error quite quickly. We have a city Winnipeg specifications for type 1A, and as you can see here, it's right at the end here, type 1A grading limits. These are the grading limits that were given by the city of Winnipeg. Now, you see something here that says type 1 asphalt ideal gradations. Call it a target gradation. With the industry, talking with the industry, city of Winnipeg, and all these years, all this data goes year after year after year, and the city has a record of it. Talking to the consultants, there is sort of an ideal gradation that if they can meet it, get very, very close to it, the other physical properties seem to fall into place. The VMA, the stability, the flow, the air voids, maximum theoretical specific gravity. So you can see here in red, 199, 82, 63. These are single numbers. But that is sort of the target that you want to hit for each sieve. And you can see the sieves here on the other side. Don't worry about this yellow here for some reason. Okay. And here I'm using the ASTM metric. Okay. 3/4, 5/8, 1/2 inch, 3/8, number 4, number 8, number 16, number 30, 200. If you like the old designations, which we shouldn't, but some still refer to. Everybody does. Anyhow, so we have the 16 millimeter crushed limestone, and you can see here just from the sieve analysis that is predominantly all material retained above the 475. You can see there's only 4% passing, so it's basically all coarse. Then we have the crushed fines. These are limestone, and you can see that 100% passes the 1/2 incher. In this example, most of the aggregates would pass the 100. Sorry, the 95, 9.5 millimeter, 100%. But in this example, we have a little bit of oversize. It is what it is. The natural fines, again, out of the Birds Hill pits, you can see here now it's quite a bit finer. See here, 60 versus 17. You got 2.6% passing. Now the crushed fines, you have a lot more because it's crusher dust. It's mostly limestone dust produced when you're crushing. And the VMA here, you can see that it's quite a bit finer. If you look at the 0.600, 38% versus 67. Now, believe it or not, and our Canadian metric, sorry, Fabian, you have a question here now. Why aren't we using Canadian metric if we were designing from City Winnipeg specs? The reason for that is because asphalt, there is no Canadian standards for asphalt. You can use these sieve sizes. Okay, we can convert these and use these limits. These limits are actually from the Canadian metric. I hear you, Fabian, and that's right. But if you're plotting, you're going to plot these against these. You're going to plot these against the Canadian metric. You're going to plot these against the Canadian metric. So you can plot the envelope in accordance with the Canadian metric sieve sizes. Your gradation here, we're plotting against the ASTM. Because when you're looking at the Asphalt Institute, when you're looking at blending, it makes that much easier to stay in tune with the industry following these. You can, Fabian, there's not a problem. You can just say, okay, I'm not going to think ASTM metric, I'm going to strictly think Canadian metric sieve sizes, not ASTM. Now for asphalt aggregate, is there a soundness test that tells you to, if you're doing a soundness test on asphalt aggregate, is there an ASTM test that tells you to use Canadian metric sieve size? There isn't. There is a soundness test in CSA for concrete aggregate following the Canadian metric sieve size. But if you read the soundness test for the City of Winnipeg asphalt, they refer to soundness in accordance with ASTM. And ASTM has no mention of the Canadian metric sieve size. So from a sieve point of view, I agree with you, Fabian. You can use, from a gradation point of view, you can use Canadian metric. But if you are doing other tests, you're going to have to do all the prep work, going back now and using the ASTM metric sieves. The soundness, LA abrasion, sulfates, everything else refers to ASTM. There is no Canadian metric for asphalt. So I don't know why the city is doing that. That answer it? You can, if you want to plot, and I'll let you guys do that. If you want to plot, you do your blend here, you can plot your envelope. These you can plot based on the Canadian metric from the City of Winnipeg's pack. If you want, we can change it, but it's going to be hard to understand when you're working with the Asphalt Institute. The 475 to 2.36 is all being referred to. And then if you want to plot this total blend, with this, it's doable. Because when you plot them, okay, when you plot them, that come out here. Ah, shoot. Sorry, guys. Oh, here it is. See, I plotted these all now, okay? Now, this is the grading envelope. This dotted red line here, guys. You can see here that I'm using the ASTM sieves. Okay. But if you want, you can use the Canadian metric for these designations. So 4.75, okay, is going to be 5. So the actual point is going to be here. Your gradation, the blend here doesn't change any. It's still plotted as 4.75, so close to 5. So it's just that when you're referring to other tests that you're familiar with and you're trying to correlate, I'll jump into 2 different sizes. So if City of Winnipeg said, now do a soundness test or LA abrasion test in accordance with CSA standard, then it's different, but they don't, because asphalt, there is nothing. It all falls under ASTM. The Asphalt Institute, which follows ASTM, or AASHTO, which follows ASTM. That kind of clarify that figure? One way around. Okay. If you look at the original, you're talking about 25 hundredths of a millimeter difference between 5 and 4.75. 2.5, okay, 1.25, 630, 315, 160, 80. Okay, 0.005 millimeters difference. So really, when MI actually writes their spec, even for concrete, they don't follow the Canadian metric sieve size. They'll even state in their specification that the ASTM metric shall be interchangeable with Canadian metric. So that way there's no discrepancy later. They'll say If you're testing against a 5 millimeter, it's the same as a 4.75. Okay, it's just that if you're talking about oranges, let's talk about oranges. But once you start throwing in apricots and everything else, it's kind of confusing. Okay, so don't worry about this. You won't have it. We physically did 1A, 1B. These are the groups that tested various aggregate sizes. Then we took the average. These are the averages. Just on the next spreadsheet. You don't have this. So physically, the lab was every group would do 2 or 3 sieves, and then I think the average of 16 millimeter. See, these 3 groups did 16 millimeters, 1B, 1C. Actually did 16 and crushed. So you typically you'd have to. Then we took the average of those. So that was just to give us an average. So now we're just looking at averages. So you don't have to worry about individuals. So here you can see we've got the individual sieve analysis. And there's no spec for the individual. CSA should actually have changed a little bit where they're now saying that individual gradations for the coarse aggregate and the fine aggregate in CSA can deviate from their individual ones, provided that a blended one combined meets the criteria for the concrete mix design. And this is what asphalt does. I worked on one project where we actually combined 5 aggregates to meet a spec. We couldn't, so we had to bring in another bin, another conveyor belt, and we actually had to do a 5-bin asphalt mix. Here, this is a 4-bin asphalt mix, 16. So these are the individual gradings. Once you have them now, we're going to shoot for a target. We'll fall in between here, but we want to shoot as close to this as we can. And this column, I just put that for myself. This gives me a plus or minus from the target. So if you look here at 53, you can see that I'm under 54 by 1.1%. These are to 1/10 of a decimal. These are 2 whole numbers. I can change these if you want to make more sense. Okay. But again, we report always to the nearest 1%. But you can see here now that this is 52.9. I'm under by 1.1. Here I'm under by 4. I'm shooting for 18. You're going to find then that you may want to try and get these in spec, and you might throw something else on. It's because of these individual aggregates, depending on their grading. I could have given you right down the middle of the pipe, and this would have worked out perfect, but I don't want to do that. You guys to think a little bit. And here again, I just put my formulas, my percentages, and these are based on those percentages. Okay. So if you're comfortable with a spreadsheet, you can do that. So I've written the individual ones. So based on this one, and this is going back 2-3 years, we determined that 19%, 35% crush fines, 3% natural fines, and 43%, which really is quite an anomaly. Typically, you don't need that much VMA sand. For some reason this year, or 2017-18, samples we got from Mulder wasn't much different in some aspects between the VMA and the natural fines. It does change here. But so typically you could have areas of only 10% VMA sand, and you may have 30% natural sand. But it is what it is. It doesn't matter. You play around with it. You shoot for that target. Now, when we're plotting gradations, I remember a lot of times you guys did a coarse sieve and you put it on a sieve sheet, then you did a fine aggregate, you put it on another grain size curve. Why? I like to see them all at once. There's all my individual ones. Okay. I got 4 individuals. My coarse. Okay, and this is my combined, and here's the grading envelope. So if you look at the legend down here, combined gradation, type 1A grading limits, red. 16 millimeter coarse aggregate is the black, and you can see here. Fine aggregate. Okay, the VMA sand, a lot finer, you can see it. and then the crushed chips or the crushed fine aggregate, which was mauve or purple. Okay, so now these give me my individuals. I've also done just a. Was on the other one I had. I just have one where I just show the blended, but I like to have all of them on one because then it shows me in relation. So if we go back here, and we change these. Okay, so let's just play around here. For example, I'm going to go 25, 25, 25. And that nomograph that you guys used last year with Natalie, where you plot sieves to come up with a blend, can be used. No two ways about it. But to me, it's a lot more work. Once you got your spreadsheet, nowadays, a lot of people just do it this way, because you can play around with it. You can look at what is contributing to this and what is contributing to that. And we're going to look at that right away. So you can see here, obviously, look at these percentages. Way out to lunch, because I just, oh, no wonder. Okay. I'm out about 5%. So if you actually looked at the chart, you can see it changed somewhat. Okay. We're going to be talking about a restricted zone at about the 0.37 analysis, sieve size. You want to get a hump in there because you want to miss what's called a restricted zone. We'll look at that a little bit more when we get into aggregates. I want to get going on this blend to get started. You can see that we're trying to get that hump. If you don't get that hump, you're going to follow what's called the maximum density line. And if you do, you're not going to get your properties. Okay. If my air voids are low, okay, I want to get more air voids into my gradation, into my sample. And I've got fine aggregate. Okay, I've got the VMA sand, I've also got the natural sands. What should I do? Should I increase the amount of sand or decrease the amount of sand? Anybody? I want to increase my voids. So should I add more sand to my mix or less? Decrease. Okay. The air voids will also be a function as to how much AC, asphalt cement, I'm going to use. So should I increase my AC also? Or should I decrease the amount of asphalt cement? You need to, okay, I've got a comment here. You need to decrease the asphalt cement. Is that what you're referring to, Powell? If I want to decrease the voids? Okay. VMA sand, if you increase, now you guys, everything you learned is all going to go out the door now. If you want to increase the voids in an asphalt mix, increase the voids. You can either increase the fine sand, increase your AC content. Is that right? Or is that wrong? You're referring just to the sand. So right, Paulo, when you're talking about the sand, you say you need to decrease if you want to decrease the voids. You need to decrease So in other words, it's the other way around, Pavel, because this is asphalt. Believe it or not, we want to get more voids, we want to fluff it out. We put more sand into it. Typically, you would say, well, to decrease voids, I got to add sand. And when we look at this a little bit better, we'll find out a little later on. So there's, when it comes to asphalt pavements versus concrete, there's some things that just don't seem right. Okay? If we want to increase voids, we increase the sand because you can't compact it. It just kind of fluffs it out. Okay? You're going to have more surface area. You're going to require more cement. So it just pulls it apart. We'll talk about that a little bit more. Okay? So these are some of the things we have to look at. So when we go back to our grading here, we can see here now that we have to adjust these. We want to be as close to these as we can. Now, if you look at the grading spec, the difference between the coarse fraction and the fine fraction is 4.75 millimeters. Okay? And here you can see 55 to 70%. So 60%, say 63% passing. Typically for concrete, we'd want it the other way around. We'd want more coarse, less fine aggregate. For asphalt, it's the other way around. So instead of having a 60-40 mix for Portland cement, for asphaltic concrete, you're going to have a 40-60. And you can see that the coarse portion is mostly contributed by the 16 millimeter crushed limestone, because that's where all the coarse is technically. Here, if you look at the fines, you've only got maybe 5% here, 1% here, nothing there. So most of the percent retained is being contributed by the 16 millimeter crushed limestone. When we're looking at the percent retained, percent passing for 7.5, we have to say, okay, that's being contributed by the down on the bottom end. If we want to increase fines, we can see what's being contributed. Basically, the fines being contributed, or the percent passing, the finer grading, is being contributed by the VMA sand. Because if you look at it, you can see here, 6% versus 23, 38% passing versus 67. So you got 67% passing to 0.6, and nothing from the coarse. You got a little bit from the crushed fines, and you got a little bit more from the natural fines. But most of the bottom end, these two sieve sizes, is being contributed by the VMA sand. So that sometimes gives you an idea where you should be. And what I like about the spreadsheet is you can play around with these numbers quickly. So 25, 25, 25, 25. Let's see what I had before. Okay, we had 19, 35, 3, and 43. So let's say we want to increase this one. We want to try and get, these are all pretty good for this, excuse me, this example. Your grading is going to be different, so you're going to have to play around with it. But if I said I want to try and get this one closer to 18, okay? And most of that, I'm at 14% passing. I want to get that up to about 18. So you think I should increase my VMA sand? Okay, say we go to 50% here. I'm going to go up 7 here. Okay, where do you think I should drop my 7? It's got to balance 100. Okay. Where do you think I should? What else should I reduce the crush fines, or should I reduce the natural fines? Say 3 and 4. So that's 3%. Say have no natural fines. I mean, you're going to have some. Well, we went up 7 here. Let's just drop this by 7, okay? So this will give us 28. We're off. We're off because look at now we're too fine. So if you looked at it, Now we're getting too close to falling out of spec. Okay. Now 0.3 here, this is a critical sieve. You should try and be up a little higher on the 0.3. That's where that hump should come in, because that's what's going to give you your VMA and air voids. It's just something we know in the industry and from the asphalt technology. Talk about 16 millimeter. Okay, Fabian. Yeah, you might be right. Let's try that. So we're going to go back. So which, okay, 16 millimeter. How much do you want on the 16 millimeter? You can use your voice, you guys. 13? Okay, we'll go 13 there. Okay. And I'm still low by 6%. Where should I make my other adjustment? Crushed. How much? 6 crush fines? Okay. So give me 34. Maybe a bit better, but we're still 7% here. We're actually out of spec here now because we're just out of spec. We just make it a 70. Yeah, right. See, it's not easy. So it's going to take a little bit of meeting. And good thing you guys are in groups of 3 and 4, because like I always say, 2 heads is better than 1, and 3 is better than 2, and 4 is better than 3. You guys are going to have to try and work this out. But you may not get it exactly. Don't worry about it. But get as close as you can. The key sieves, okay, when we're going to be going with the mathematical formula for determining combination, say, on 3 aggregates. Your main control sieves are the 475 that are important, and for your additive, anything finer than 075. These are the 2 that you start off with as starting points. And we're going to look at that formula a little later. It's loaded on assignment. You can go through it if you want. Read up on it. I gave you the solution sheet, but the formula there is given to you and what it tells. And with that, what you're trying to do is when you're using 3 aggregates and you're using that formula, you're going to set up a target. And I usually set it up down the middle. And when we go through it next week, it'll be self-explanatory. This year, again, you won't have that. We found that if you meet your target, these are roughly plus or minus. It doesn't always occur that way, but you should have 4.4% air voids. Your VMA is going to be 14. Remember, we need a minimum of 14. You got to be between 3 to 5 on the air voids. We're 5. You got to be between 5 and 6 for the AC. We're 5.3. So for the city of Winnipeg, most asphalt mix designs are running 5.25, 5.3, 5.35% AC. And that's where contractors usually like it, because that's the most expensive part of your mix. A lot of the control charts you're going to see, we're going to graph all these things after. We have to graph them to determine the optimum mix. Once we get into the asphalt mix design, you'll understand that. When you do an asphalt mix design, you're actually going to batch hot asphalt under 5 AC contents, 4, 4.5, 5, 5.5, 6. And you compact 3 briquettes for each one, 3 asphaltic specimens. And you're going to run stability on each one of them. You're going to run air voids on them. Well, air voids are calculated from your bulk specific gravities. You're going to run bulk specific gravities on them. Then you're going to take your hot asphalt mix and not compact it, but you're going to let it set up, and you're going to break it up, and you're going to run a maximum theoretical specific gravity on it. Just like you've done specific gravities in B109 using the vacuum pumps and the glass picnometers. Well, this time we're going to use the big pots for AC. And you're going to do the same thing. You're going to put under vacuum. You're going to suck all the air out. You're going to determine the GMM. What's my maximum theoretical specific gravity of my mix? G is specific gravity. M is mix. M is maximum. That would be a mix that had no air voids in it. Okay, so these are, and from all this, you plot after. And we're going to get into this a little bit more later. I'll have other spreadsheets. You're going to summarize all this data, and then you're going to graph it. And off that graph, you're going to pull, just like plotting a Proctor curve. Off the Proctor curve, you can pull your optimum moisture content that gives you your maximum dry density. You're going to be able to plot your AC content that gives you air voids between 3 and 5, and we usually use 4 as the middle. Okay, 4, as you can see here. Anyhow, I'm getting a lot ahead of this, but for the next lab, I want you guys in Unlearn, you got group 1 and group 2. You're given gradations of your aggregates. So if you're in group 1, you use, and then you come up with the blend. And you're going to try and shoot for your target as close to it as you can. I don't know what these gradations are from my memory. I got to go back into Learn to see what I gave you guys. These were taken back from 2017 and 2018. And these were physically determined in the lab. That's what we would have done had we had it. And down here, you can see the properties of the aggregates. And here you can see that these properties of the aggregates are weighted averages based on these combinations. If these change portions, these individuals change accordingly to give you a blended. So if you physically took this material, if you physically blended it together, 13%, 34, 3, 5, and separated the coarse from the fine and ran specific gravities, physical tests on the coarse portion and on the sand portion, you would get these values. So there's your specific gravity bulk. Okay? S stands for stone, G stands for specific gravity, bulk is bulk. That's oven dry. Sorry, GS apparent is oven dry. This is saturated. Remember, saturated surface dry? And GS is the apparent, and we'll get into these definitions a little bit more. These are critical, and then your absorption. So these are water absorptions of your aggregates. So the blended one obviously is a weighted, but how much coarse you use. In this case, the coarse has 2.1. Fresh fines has 2. If you use more or less of the other one, it's going to change these. So again, I've just plugged my formulas in here, mathematical. So, any question on this? So write up a letter report. Now I'm going through lab 5 on your concrete, and I'm almost completed. By now, you guys should be able to write a letter report. Some of you are still not knowing how to set up your reports. If you're not going to use a fictitious letterhead, you got to tell me who the sender is and the address. Then there's me, who you're sending it to, name and address. Then there's a closure, group 1B, boom, 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 3 or 4 names. And typically you'd sign above them. If you're going to use a letterhead, for example, like a fictitious company name, again, you got to have an address. And the second page should tell me that who the letterhead is. You may not need that big logo that you guys are coming up with, but on the bottom of the second page or wherever you want, that's more artistic than anything. You should at least state in writing. You don't need the big logo or the company logo. Just name and address. I have to know who that second page is from. I've been very lenient on spelling and grammar, sentence structure. You have to pick up on that. You're going into industry pretty soon. You got to know how to write. There's nothing worse than a client getting a report from another consultant with names misspelled, words misspelled, sentence structure, grammar not there. It may not be your strong point, I realize that, but it's important, guys. I'm going to start marking for layout. If you don't know how to write a letter report, go back to your textbook. First year, technical communications, go online. There's lots of textbooks out there, but it should give you, and I know the styles have changed, but you still got to have proper structure, proper grammar, proper punctuation. Okay? I've been basically lenient on that. I'm going to start, for this go around, I'm going to be maybe deducting half a mark to a mark. Okay? Guys, believe it or not, you're going to be writing a lot of reports when you get out. Project's not done, work's not done till the paperwork's done. Remember that, okay? Anyhow, this is the spreadsheet. These are the 4 aggregates. You can set up whatever. I gave you just a basic value. I didn't give you an Excel spreadsheet or anything. How you determine it is up to you, but make it presentable. Put a title on your attachment. What's it about? I've had in lab 5, some of you guys use the mix design that we did for lab 4. Some of you changed that, which it should have been. Because now you're giving me compressor strength and flexural strength results. You're referring to the trial mix attachment. Yes, you've included everything, but really, lab 5 is not trial mix design. It's not trial batch weights. It's concrete compression and flexural strength. Try not to get into a habit of straight copying, guys. Look at it. Does it make sense? Is my lab data that I'm using, does it pertain to what my report's about? Okay? Don't try and copy everything you see, because sometimes it's not applicable. And I don't change it for a reason. Just to see if you guys are going to change it. And like I said, I haven't been overly tough on it, but I'm not going to be as lenient now. I'm your client. When you're writing this report, yes, you're writing it to me as an instructor, but keep in mind, I don't know anything about it. So don't cloud my head with trivia, but give me the facts, summarize it, refer properly to an attachment. Are they in chronological order? Neil Chandler, before Elena took over, when you had those lab information sheets from last year, if they weren't in the proper order, he would not accept it. If you had your data sheets first and then your lab information sheets behind it, it's not a chronological order, he would not accept it. 0. Makes sense. You're going to send data with the covering letter stapled to the back of everything to your client? That's what it looks like. So we're trying to stress the fact that you have to show professionalism too, okay? So try and get the grammar. And I know some of you guys aren't getting somebody to review it. Because if you're telling me 4 review it, and 4 don't pick up spelling errors, and 4 don't pick up sentence structure, 4 reviews don't pick up the wrong data, then I don't buy that. Maybe 2 can miss it, but not 4. If you're doing a proofread and you're actually looking for quality and content, 4 can't miss it. 3 can't miss it. Someone's got to catch it. And if you don't, then you're not doing a good job. Coming across as being kind of harsh, but that's the fact, guys. You're going to be putting out reports there. Clients paying you $250 or $200 for a sieve analysis. You should at least be given $250 worth of a good quality report. And that includes spelling and sentence structure and grammar. If in doubt, check. There's numerous texts out there about sentence structure English. If you can write, you'll always have a job. You'll always have a job. Okay, enough said. I'm rattling on. Any questions on the spreadsheet here? Yeah? If you have some, just send me an email. Later on, we're going to be going to something like this. See, when you come up with the actual blend, someone's going to say, well, I'm just going to take from my actual mix design, I'm just going to take this aggregate, and I'm going to take this aggregate in a separate pan, and I'm going to take this aggregate and this aggregate. Then I'm going to weigh out 13% of this material, and 34% of this material, and 3% of this material, and 50% by weight of this material, and blend it together, and I got my mix design. In theory, that's the way it should be, but that's not what you're going to do. You're going to now start separating each one of these into various test fractions. So in other words, one of our labs, not a car seat, at B109 was, I called it a dust lab. there was dust floating around like you wouldn't believe. Each group would physically have to sieve out these fractions. So you went to the 16 millimeter coarse aggregate and you sieved out material passing the 19 millimeters, but retained on the 9.5. And then whatever passed the 9.5, you sieved it over the 475 and kept it. And then whatever passed the 475 and sat on the 236, you kept it separate. And then whatever passed the 236, you kept it separate. And you did the same for this, and you did the same for this, and you did the same for that. Then you would go back and say, well, I need a total of 1,200 grams of aggregate. Of that 1,200 grams, 13% is crushed limestone. This 13% is now going to be made up of a certain percent of this fraction, and a certain percent of this fraction, and a certain percent of this fraction. So we're going to get into that more in the other lab. So you actually have to physically separate that aggregate, and then throw it back together, dry it, and then you're going to add the AC to it. Now, it's not done like that at the batch plant. They've got big bins, and they calibrate the gates and the speed of the belt. But for a Marshall mix design, you're going to break down each material into certain sizes, and then you're going to individually weigh out those sizes, blend them back together for more control. You're trying to hit this target gradation really bang on. Okay, so keep that all in mind when you're looking at this. This is going to be the next step. You don't have this yet. Okay, any questions? There's a lot to asphalt compared to concrete. Okay, if there's nothing, let's call it a day. If you have any questions, again, let me know. And your gradations are given under group 1 and group 2 in lab 1, lab 6, I should say. I think this is identified as lab 6. I just continued. No, lab 1A? Wow, whatever. You'll notice it's under asphalt labs. Anyhow, I can't even remember. I've changed the course so much. Okay? Any questions? Done? Okay, we're done. Good one.